Hello everyone. The topic of our CRE lab assignment group is isothermal PFR. So the aim of our experiment is to determine the conversion in PFR for saponification of ethyl acetate with sodium hydroxide at fixed temperature. So basically we have one more objective in this topic, that is to study the effect of temperature on the reaction constant K and determine the activation energy. So the aim of our experiment is to determine conversion, rate constant K and activation energy. So this is the overall introduction of our experiment. So next is utilities required. So first of all, we need electricity supply. Electricity supply should be single phase 220 watt alternating current. The frequency should be around 50 Hz and the current it should range around 5 to 15 amperes. And the condition for it is that the current should be combined socket with earth connection. Then basic other needs are we need water supply, then we need flow drain, then also we need floor area of around 1.5 meter to 1 meter. Then again in laboratory there are various utilities which are required. So the apparatus are conical flask. There should be two conical flasks of 250 ml each. Then we need two measuring cylinders 50 ml each. Then next we need one burette of 50 ml with stand. The burette should be with stand. Then we need beakers. Beakers should be of 250 ml. Beakers should be also 2 in number. Then we have one funnel. So these are the basic utilities that are required in the laboratory to perform this experiment. So next is chemicals required. So the chemicals required are 0.1 normal sodium hydroxide NaOH. We need 0.1 normal NaOH and the volume of NaOH should be around 20 liters. The next chemical which is required is 0.1 normal ethyl acetate. So ethyl acetate should also have volume same as 20 liters, around 20 liters. Then next we have 0.1 normal hydrochloric acid. The volume of hydrochloric acid is slightly less, that is 0.5 liters. So these are the three chemicals required. Apart from this, we have one more indicator, that is phenolphthalein indicator. We should add only few drops of phenolphthalein indicator, that is 2 to 3 drops. And also the property of phenolphthalein indicator it is that it changes the basic solution to pink color, and for acidic solution it turns the color to colorless. So this is the basic property of phenolphthalein indicator, and these are the basic chemicals that are required in our experiment.
So, welcome to the CRE lab. So, here we are with isothermal blood flow reactor. We can clearly see that we have two overhead tanks, two storage tanks, two rotameters for controlling the rate of fluids that chemicals we are using for reaction.
So hello everyone, myself Samir Tasildar. So let's proceed further. So this is a temperature, so this is a controller board. Here we can see we have a main switch which directly controls the power supply. Here with the help of this we can on and off this power supply. Next we can see we have two switches for both the pumps, pump 1 and pump 2. With the help of pump 1 we can on and off the flow rate of the overhead tank 1. This is overhead tank 1. And we have second overhead tank for which we have switch 2. With the help of this switch we can on and off the same thing. Then further we can see we have a heater switch. With the help of this switch we can on and off the heater. It the same function as these three with the on and off. Then further we can see it is a temperature board. In this temperature board, the red one indicates the current temperature, which is the current temperature of the reactor. Then also we need a desired temperature to which the temperature should be taken. For that we have a green one. This is a set point temperature in which we set the temperature which we want. Next we can see three small switches behind this board. The first switch is up, which is basically if we need to increase the temperature, we use this switch. Then we have a down switch. Down switch is basically used to reduce the temperature. Then we have a mode switch, that is to fix the temperature which we need. So basically this is the work of this temperature board. Then further we can see agitator reactor. In this agitator reactor also we have a small on and off switch with the help of which the agitator gets on and off. Then we can see there is a regulator. This regulator is used to regulate the speed of the agitator. This regulator is used to regulate the speed of the agitator, and this varies from 10 rpm to 100 rpm. Preferably we use 80 rpm for the reaction to take place. So let's proceed further. This is our reactor setup. So this is an agitator. We have two inlet pipes. Then we have a PFR plug flow reactor. Then we have a tank. At the bottom of the tank we have a heating coil. So now let's go one by one. we can see two inlet pipes. These two pipes are for the two reactants. One is ethyl acetate and one is for sodium hydroxide. So these two pipes are directly connected to two rotameters. So these reactants enter the PFR. PFR is made of cylindrical pipe and thus this PFR is coiled to reduce the floor area. As you can see, the PFR is coiled so as to manage the space and reduce the space. Then the reactants react inside the PFR. When the reactant enters, we start the time and approximately wait for 1.5 times of the residence time until the steady state is achieved. Then further, we can see this is an outlet pipe which is used to collect the sample titrations.
So next we have chemical reaction. So the chemical reaction which is involved in this experiment is ethyl acetate, which is reacting sodium hydroxide to give sodium acetate and ethyl alcohol. The reaction is given below. So here we can see CH3COO-CO2H5, which is ethyl acetate. It reacts with NaOH, sodium hydroxide, and the products which are formed in this reaction are sodium acetate, CH3COONA, and C2H5. This is ethyl alcohol. So this is a second order chemical reaction, and the rate constant for this chemical reaction is given by this one, which is minus Ra, which is equal to KCaCb, where K is the rate constant. Ca and Cb are the concentrations of A and B. Next we have Ca0 is equal to Cb0. This is basically the assumption where the initial concentration of A and B are equal. So after discussing chemical reaction, let's proceed further to theory. So before going to plug flow reactor, let's actually see what a plug flow is.
In fluid mechanics, plug flow is a simple model of the velocity profile of a fluid flowing in a pipe. In plug flow, the velocity of the fluid is assumed to be constant across any cross section of the pipe perpendicular to the axis of the pipe. The plug flow model assumes that there is no boundary layer adjacent to the inner wall of the pipe. The plug flow model has many practical applications. One example is in the design of chemical reactors. Essentially, no back mixing is assumed with plugs of fluid passing through the reactor. This results in differential equations that need to be integrated to find the reactor conversion and outlet temperatures. Other simplifications used are perfect radial mixing and a homogeneous bed structure. An advantage of the plug flow model is that no part of the solution of the problem can be perpetuated upstream. This allows one to calculate the exact solution to the differential equation knowing only the initial conditions. No further iteration is required. Each plug can be solved independently provided the previous plug's state is known.
So after seeing what plug flow is, now let's get back to plug flow reactor. So you can see a basic plug flow diagram is shown on the board. So here, in an ideal plug flow reactor, there is no mixing in the direction of flow. This means that the mixing does not take place in this way. The mixing takes place perpendicular to the direction of flow, which means the mixing takes place in this direction. So there is no mixing in axial direction. So this is the meaning of these 2 points. Next we can see concentration of the reactant varies along the length of the reactor and not in radial direction, which means concentration varies along this length of reactor. It does not vary in this direction. So this is the meaning of third point, which means concentration is varying along the reactor. So some basic symbols we can see where V denotes the volume of reactor, V denotes the volumetric feed rate. Then we have Ca0. Ca0 is the feed concentration of A. Then we have X. X is the degree of conversion. So let's move further. In general, we used to use long type of cylindrical pipes for plug flow reactor. We can see we use this type of plug flow reactor. Long cylindrical pipes were used for the experiment. The problem with this type of plug flow reactor was that it consumed more surface area than needed. So to come out of this problem, we had many experiments. Then we came up with the idea that to use coil type reactors. That is, this cylindrical type of plug flow reactor is arranged in the shape of coil. The advantage of this move was it reduced the floor surface area, and we can use more type of cylindrical pipes in less surface area. So So this is the same point which is written here, that in case of a coil, turbulence is introduced due to frequent change in the direction of flow. So here you can see the direction changes every time in a tube. Due to this, turbulence is created inside the reactor, and this created in the direction of flow and in the presence of secondary flow. The next point, that due to this type of turbulence, we expected a higher value of K in case of coil type PFR. So this type of coil type PFR, we expected higher value of K.
So after discussing theory in detail, let's proceed further to procedure. So this section of the video, it will guide you through a step-by-step procedure for conducting a reaction in a continuous stirred tank reactor or CSTR with NaOH and ethyl acetate. So let's see step 1. So step 1 is basically preparing the solutions. So we start by preparing our solutions. First of all, we dissolve 80 grams of NaOH in 20 liters of water. 80 grams NaOH in 20 liters water. So this we are doing to prepare a 0.1 normal NaOH solution. Similarly, we prepare 0.1 normal ethyl acetate solution by mixing 176 gram ethyl acetate in 20 liters of water. By doing this, we get 0.1 normal of ethyl acetate. So after this, we proceed to the next stage. The next stage is basically pouring solutions into their respective tanks, that is ethyl acetate tank and NaOH. We pour 20 liters of prepared solution ethyl acetate in this tank and NaOH in this tank. So after preparing the solutions, now let's proceed further to step 3. Step 3 is setting up the water bath. That is, we have to fill the water bath with water and then set the desired reaction temperature. That is, this is the water bath and we need to fill it with water, and then we have to set it to a desired temperature. So as we have seen in the laboratory, we have a control board which is set up on the apparatus. The red one denotes the current temperature, which is the temperature of the reactor. Then we have one more section of green board. This basically represents the desired temperature, the temperature to which we need to reach. So after filling this water bath with water, we set a desired temperature and we keep look on the current temperature. When steady state is achieved, that is when we reach to desired temperature, then we need to wait. So after setting up the isothermal conditions for this PFR, let's move further. The next step is preparing feed tanks. First of all, we can see these are two respective storage tanks for ethyl acetate and NaOH. So we start the pumps to flow the solutions to overhead feed tanks, which is from ethyl acetate storage tank, it will flow to its respective overhead tank. The same with NaOH, they both have their respective overhead tanks. We first ensure the tanks overflow before continuing. Once the tanks start overflowing, we then proceed further. After that, rotameters come into picture. The role of rotameters is that using rotameters, we can adjust the flow rates of both the streams. So we can adjust it accordingly so that they are equal. For example, we can see that if we maintain a flow rate of 10 lph, we have to achieve the equimolar rate. So in this way, we can use both these rotameters, and both the rotameters flow rate should be equal to achieve equimolar concentration. So after setting up equimolar flow rates, now let's proceed further. So the next step is achieving steady state and sampling. So now we will allow the reaction to proceed for approximately 10 minutes or until twice the residence time of the reactor, whichever is longer. This is to ensure that steady state has been achieved. So now we will collect, after 10 minutes, we will collect 20 ml of a sample. That is, we will collect exactly 20 ml of sample from the outlet into a graduated cylinder. containing 20 ml of chilled 0.1 N HCl. That is, we'll collect 20 ml of this sample into a cylinder. It will contain 0.1 normal HCl. So after collecting the sample from total sample, we now move further. The next step is the titration. Titration we need to do very carefully. So we need to transfer the 40 ml of the combined solution to the titration flask, that is the 20 ml which is collected from PFR and 20 ml chilled HCl which is present in the cylinder. We will transfer this 40 ml combined solution to a conical flask. This will contain 40 ml of the combined solution. Now this 40 ml of combined solution, we will add 2 to 3 drops of phenolphthalein indicator. We will add 2 to 3 drops. After adding 2 to 3 drops of phenolphthalein indicator, we will now start to slowly titrate the excess HCl solution using n by 10 NaOH from the burette. Now this titration should be done carefully, and so while doing this titration, a point will come where the entire 40 ml solution will change from colorless to pink. So that point on the burette is, we note it as the end point of titration. This end point of titration is basically labeled as the volume of NaOH used. So by performing this whole experiment, we get one reading of the volume of NaOH used. So similarly, to get precise value, we need more readings of volume of NaOH used. So to get that, we do some changes in our experiment. Not in the experiment, we do some changes in our conditions. So we change our desired temperature. Once we change our desired temperature, then we repeat the whole experiment. Whatever the procedure has happened till now, we repeat all the steps, and then we get one more value for the volume of NaOH. Similarly, we repeat this many times and we get all the readings for volume of NaOH.
So after the procedure, let's move to observation and calculation parts. So starting with observations, we have to observe the following points in the laboratory: volume of HCl taken, volume of NaOH used in titration, and also the volume of PFR and concentration of NaOH and HCl used. Now after the readings, let's move further on, go to calculation of Ca. That will be given by moles of HCl used divided by volume of sample. Now for volume of HCl used, let's denote it by NHCl(R) and this by volume of sample. Now NHCl(R) is equal to given by number of moles of HCl present initially minus moles of NaOH used. Moles of HCl present, let's denote it by NHCl0, will be given by volume of HCl into concentration of HCl and moles of NaOH used, let's denote it by N of NaOH. Let's say it's given by volume of NaOH used into normality of NaOH. So NaCl reacted comes out to be volume of HCl into concentration of HCl minus volume of NaOH into concentration of NaOH. Now substituting this into equation of concentration, we will get Ca equal to volume of HCl into concentration of HCl minus volume of NaOH into concentration of NaOH and whole divided by volume of sample. So here for concentration of A, we will require moles of HCl used, moles of volume of sample. For moles of HCl reacted, we will first take out. So after the calculation of Ca, let's start the calculation of rate constant K. So for steady state PFR, performance equation is given by volume upon molar flow rate integration of dxa upon rate of equation. For the reaction ethyl acetate with NaOH, let's assume it as B, NaOH as A. So rate will be given as K Ca into Cb, but initial concentration of sodium hydroxide and ethyl acetate are same, so Ca naught is equal to Cb naught. This implies that rate becomes K Ca square. Now Ca is equal to Ca naught into 1 minus Xa, Xa is conversion, and Fa naught is equal to V naught into Ca naught, where V naught is the volumetric flow rate. So our performance equation turn out to be Va by V naught into Ca naught is equal to 0 to Xa dxa upon K Ca naught square 1 minus Xa square. After taking K Ca naught square out of integral, we get V by V naught into Ca naught is equal to 1 by K Ca naught square and integration of Xa to 0 dxa 1 minus Xa square. So this integration will come out as 1 by 1 minus Xa and integrating from Xa to 0, and here Ca naught will cancel out one Ca naught, so our equation will become V by V naught is equal to 1 by K into Ca, and which after solving this we get 1 by K Ca naught into Xa upon 1 minus Xa. So from here final value of the K will be Xa upon 1 minus Xa into V by V naught. So after the calculation of rate constant, now let's come to calculation of activation energy. So for the activation energy, let's start with Arrhenius equation. which is given by K is equal to K naught e power minus EA by RT, where E is activation energy, R is universal gas constant, and T is temperature in Kelvin. K is our rate constant. So for activation energy, K1 is equal to K naught e power minus EA by R T1, and K2 is equal to K naught e power minus EA by R T2. Mention it as equation 1 and taking it as equation 2. Dividing equation 1 by 2, K1 by K2 is equal to e power minus EA by RT1 plus EA by RT2. This implies that K1 by K2 is equal to e power minus EA by R 1 by T2 minus 1 by T1, taking log on both sides. So log of K1 by K2 is equal to log of e power minus EA by R 1 by T2 minus 1 by T1. So from the property of the log base e power x is equal to x, we will get log of K1 by K2 is equal to minus EA by R 1 by T2 minus 1 by T1. So rearranging the equation, we will get log of K2 by K1 is equal to EA by R 1 by T2 minus 1 by T1. So after substituting all the values, we can find our value of EA.
So now let's look into precautions and maintenance instructions. The first precaution is that we need to measure the exact volume of water and we need to weigh all the chemicals properly. Second, we always need to use clean water and good quality of chemicals and standard solution for titration. The water we use should be clean. Next, we need to use electronic balance for weighing chemicals. We should not measure it approximately. All the measurement should be accurate. And we should not mix all the droppers of different chemicals. If we mix them, we might get a problem at the end of the reaction. The value which we need won't come. Next, we need to keep close all the drain valves and vent valve should open while filling the reactant in feed tanks. The next precaution is that the flow should not be disturbed during the experiments. If it gets slightly disturbed, the reading which we need might not come, which will trouble us in the problem solving while solving the numericals or while making the graph. So all the flow which is happening during the experiment should be constant and should not be disturbed. And the last and most important precaution is that we need to handle all the chemicals properly and with utmost care, because if we interchange one or the other chemical, all the procedure might get wrong and we need to repeat the whole procedure. So these are some of the precautions which we need to take care of. So now let's go into troubleshooting. Troubleshooting basically the problems which we might face while performing the experiment. So the first one is that if any type of suspended particles are come into the rotameter, then the solution for this is that we need to remove the rotameter and clean the tube and fit that at its place. So basically just clean the rotameter if any problem occurs. So the next problem which we might face is that if there is any kind of leakage, then we need to tighten that part or remove that and fix that again after wrapping with Teflon tape. So this we can do if there is any kind of leakage. Next problem which we might come across is that if the rotameter is fluctuating more than its average value, then we need to just tighten the control knob of that, then it will be fixed. And the final problem which we might come across is that if DTC display 1 on display board, it means that the sensor connection is not okay. We need to tighten that. And the final troubleshooting is that if we switch on the heater but temperature can't rise, but the panel is showing LEDs on, it means that the bath had burned. We need to replace that. So these are some of the problems which we might come across, and the solutions to all those are explained very well.